So hi everyone, my name is Praveen. Now in this video I'm going to explain about the constant folding, which is a code optimization technique in automata. Coming to the topic, coming to the code compiler optimization. So it is nothing but a process where the compiler transforms the code to make sure it runs faster for the better efficiency and uses the less memory and also consumes the less power without changing the functionality and the program behavior. And also there are multiple code optimization techniques in this. Some of those are dead code elimination, loop unrolling, inlining, and common sub-expression elimination, and also constant folding. And why we need compile optimization means for fast execution so that the programs run faster and quicker, and also for less memory to reduce the usage of memory, and also overall for better code quality. If you use the constant folding code optimization techniques, it generates the cleaner machine readable code. Coming to the what is constant folding. Constant folding is nothing but one of the code optimization technique where expressions involving the constant values like any arithmetic values, the constants like 5, 2.0, and constant values are evaluated at the compile time itself, not at the runtime. So the compiler optimization evaluates the constant expressions in the abstract syntax tree. We know the structure of compiler, right? Once the tokens gets generated in the phase one, later its abstract syntax tree gets generated and fix the grammatical errors in that. So in this abstract syntax tree, the optimization pass and then replaces them with the computing results. For example, let's say there is a variable x with each assigned as 3 into 4 plus 2. This is an arithmetical expression which value is equal to 14. So it stores it immediately so that the CPU never wastes time computing the result at the runtime. And here we can see the before and after. Before that, x equal to 5 into 4 plus 2, which is arithmetically equal to x equal to 22, which we have demonstrated in after case in constant folding. So these are some examples. The compiler pre-computed the all values at the run, and then just the CPU does not. The CPU does actually does it simply loads the constant arithmetical operation, so that it won't have to perform any arithmetical operations spending time at the runtime. Here are some more examples shown with the possible arithmetical expressions, logical and Boolean expressions. The compiler handles all these at the compile time itself so that it don't waste time in runtime and waste CPU cycles. They are like directly in the library. And also, why do we need it means, for example, let's say runtime performance. If we use the constant folding, there would be the better runtime performance so that the CPU does not waste any time in computing the result. It spends time only on necessary things. So CPU does not have to use any base cycles calculating the values that are already known to it. It simply loads the final result. And also smaller code size. If we pre-compute the values in beforehand, then the code size will be less, and also better readability. If we use constant folding, it gradually decreases the code size and then eventually improves the readability of the code, and also a better optimization technique. And coming to the way we would use this technique means in optimization technique. In success compiler, we do there are multiple cases like lexical analysis and syntax analysis and semantic analysis, intermediate code generation, and optimization, where we perform here we perform the constant folding, and then later the code generation gets happen, and the target code we get it to after the final phase. So in these phases, the fifth phase, the optimization happens here, where we apply the constant folding here. Coming to the how constant folding works. Here first the past expression. For example, let's say in x equal to 3 into 4 plus 2. This expression that's converted to AST first, which is abstract syntax tree. Here the nodes are it is represented implies 3 comma add implies 4 comma 2. So here we have to identify the constants first. In this expression, the constants are 3, 4, and 2. Here, first the compiler checks all the leaf nodes, which are constants or not. If it is yes, uh, 3, 4, 2 are literals here. So it will, and then it will evaluate from bottom to up. It will evaluate inner expressions first. So inner expressions would be the add of 4, 2, which is 6, and then it will be multiplied with 6. So 6 multiplied with 3 is 18. Then it will be replaced with abstraction type tree. The entire set subtree the result is now it's converted to x equal to 18, which is now after the constant folding exchange decreases the size, improves the readability. Coming to the real life analogy, we will use it in multiple places. I mean, in everyday life also. Some of the examples are supermarket billing. Before the customers arrive, the manually we have to have 25, 50, 75 at each checkout, I mean, for each particular thing. Once the cashier pre-computes the total, it will become 25, 50, and 75 would be 150. So the customer reaches to the counter, and then with the help of pre-computation, it saves the time at the billing counter. That is a one example. And also math teacher's trick. Before the student types by ask where as the area of circle, you can solve it during the exam with the pre-computational area. If you have 78.5, it will fix the answer directly without spending much time. And there are multiple other examples like SP preparation before and after. Uh, if you know the measure of the curve in beforehand, it would save our time. And the applications in compile and computation. So, like I mentioned earlier, faster program execution, reduced runtime overhead, efficient memory usage, and also cascading optimization effect. Coming to the faster program execution, it will limit the arithmetic operations at the runtime, right? So CPU loads the pre-computed constants in beforehand, so that it eventually leads to reduce instruction count in binary, and also improve the loop performance. And also we can say that through the runtime overhead is cut off. There will be fewer CPU clock cycles have been used, and compared to low power consumption is happening if we use the constant folding in our core optimization technique, and smaller instruction cache pressure will be there, and better branch protection. And also, instead of storing multiple variables for each computation, if we use constant folding, it will be stored in the data section, which have no stock allocation for each temporary results, so that it will be smaller generated binary size for better cache utilizations also. And yeah, coming to the limitations, there are multiple limitations. Now let's see some of them. When we use a constant folding, there are some limitations that cannot be applied. Suppose let's say variables are involved. If in a equals to x plus 5, here the x is a variable, it is unknown at the compile time, right? So the value of x depends on runtime input. So the compiler cannot execute beforehand. So in this case, constant folding cannot be applied. And also when the function calls with side effects, side effects means here we have to read something from the file, so which takes time and it cannot be completed at the compile time. So here in this call, when there are side effects, and also when there is an overflow, it cannot store the value. So in this case also it can't be used, and also pointer and address expressions. Memory address are only known at the runtime, right? So we can't do this at the compile time. And input output system calls. If you are using a function that is calling input output hardware sensor like the runtime, any value at this time comes from external sources, so it cannot be completed beforehand. So constant folding cannot be applied here. So these are some situations where constant folding cannot be applied. Yeah, when the variables are involved, anything that is required at the runtime, in those cases constant folding cannot be applied. And yeah, we can here have demonstrated a differentiation between constant folding and constant propagation. In constant folding, it evaluates the constant expressions, where in constant propagation, it tracks variables values across the code. So here we can understand with an example. Here in code for constant folding, x equal to 3 into 4 plus 2, which is becomes 14. And here in constant propagation, x is initially at 5, and we use the x in for to get the value of y. Then y equal to x plus c, it will be 5 plus c as 5, but we are using x value in beforehand. So it uses the data flow analysis. But in constant folding, it uses the abstract syntax tree. It works on single expressions. In constant propagation, it works across the multiple sets. That's it. And coming to advantages and constant folding, there are multiple advantages. Some of them are improving the performance. The programs get executed faster as if you skip some cycles, unnecessary cycles, by performing automatic operations. Constant values are directly loaded, right? So no computation is needed at the runtime, and also the CPU usage, since the CPU cycles are reduced, so eventually reduced CPU usage will be also reduced, and smaller binary size. Elimination of computation means fewer instructions are generated, and if fewer instructions are generated, then smaller binaries are loaded faster, which uses the less storage and cache memory. And also it enables the further optimization technique, and runtime cost will be almost zero since it makes it fast since we know the value beforehand. And also it's systematically safe as well since it never changes the program behavior, and the result is always mathematically identical to the original expression. And limitations are, as I discussed earlier, these are the big limitations where the values depend on the user input means at the runtime, and also variables that change at the runtime, and the function that calls with side effects like reading from a file. And here we can with the visual diagram. Source code consists of A as 4 into 8, which is 32, and B is A plus 10, W plus 1 is 42. So and C is 2 plus 5. So here the in abstract syntax tree, we are performing for A multiplication of 4 into 2. Here these nodes are 4 and 8. In constant folding, these 4 gets multiplied, and in abstract syntax tree and becomes 32 as the only node. Then, so in summary, let's conclude why, and when we need the constant folding. So basically, what in the sense it's pre-computed the math and logical expressions during the compilation process, and why we need it to reduce the program size and improve the performance and efficiency of the program, and when means during the optimization phase in the structure of compiler. Before the machine code is just generated, we have to optimize it, and for that optimization, we use this concept for it. And coming to the conclusion, what we have learned in this constant folding means it's a compile time optimization technique where the compiler pre-evaluates the constant expressions and gives the value to source code that eliminates the unnecessary runtime mathematical logical boolean any expression, and eventually reduces the CPU workload as well. That results in faster and more efficient program with zero change in behavior, and it's systematically safe and secure. Works by evaluating the expressions initially, where all operands are compiled and functions, and then it is applied during the optimization phase, and it produces the faster results and in binaries with fewer runtime operations, and cannot be applied when variables are dependent on runtime environment, or system calls are generated, and often combined with constant propagation for maximum effect. We have discussed about the constant propagation, where we use the multiple segments. Yeah, this is all about constant folding. Thank you. Thank you for giving this opportunity.